Hello everyone, I am Mousumi Rizia, a PhD student at University of Texas at El Paso. Today I'm going to present my project titled Transient Thermal and Static Structural Analysis of an Additively Manufactured Part under Extreme Temperatures. This presentation is done as partial fulfillment of the Computational Mechanics course held in spring 2019. I will be following the sequence as shown on the screen. This project focuses on studying an additively manufactured part subjected to two extreme solar radiation cycles in low Earth orbit space with the new additive manufacture tool of ANSYS 2019 R1. Two coupled simulation studies have been carried out. First, transient thermal analysis to see the effect of two extreme radiation temperatures on the build parts, and then static structural analysis to find out structural effect on the build part caused by the additive manufacture process. This project is also part of a pilot research to study 3D printing in space that is currently under consideration at CSETR of UTEP. Additive manufacturing technology is rapidly developing since its introduction in the 1980s and spreading to almost every sector today due to its inherent capabilities. It has truly transformed and revolutionized today's design and manufacturing sectors, offering enhanced performance and custom capabilities in almost every sector known. According to Siemens, the technology is a game changer, with benefits including a 30% cut in greenhouse gas emissions, a 63% reduction in resource use, and a shrinkage of the time it takes to bring products to market by 75%. Thanks to improved design flexibility, components that could take 2 years to progress from drawing board to factory can now be designed, tested, refined, and perfected within weeks instead, and they are of higher quality than those they replace. As mentioned earlier, additive manufacturing is spreading rapidly, and now it's time to apply it to the space. Consider this, it takes $2 million for a single brick to be shipped to the moon. Considering such prohibitive transportation cost, a 3D printer would definitely prove to be cost-effective and produce items as and when needed, which would no doubt improve operational capabilities in space. However, in order to reach that stage, we need to overcome the challenges of the space. Of the challenges, this project will deal with the extreme temperatures caused by solar radiation. Already, NASA and some other organizations are taking steps to counter the challenge. In 2014, NASA scientists aboard the International Space Station 3D printed a ratchet wrench for the first time in human history, using a CAD file transmitted from NASA's Marshall Space Flight Center in Huntsville, Alabama. Later, 24 other parts, featuring 14 unique shapes, were printed that were pre-programmed into the printer before it left Earth. You can see the 24 parts on the right side of the screen, and all 25 parts were returned to Earth in February 2015 on the SpaceX Dragon. 316 stainless steel is chosen. It is a popular space-grade material that has the ability to withstand high temperatures, atomic oxygen, and other features as well that are critical in space engineering. The provided material library by ANSYS contains 6 materials typically used in metal additive manufacturing, including our selection 316 stainless steel. For additive manufacturing thermal and structural analysis, material property requirement is a little different. Thermal conductivity, density, specific heat, elasticity, plasticity, etc. All of the properties need to go all the way up to the melting temperature of the alloy, because each layer introduced at the melting temperature. The assumption here is that in the layer there is no overmelting or undermelting of the powder. The entire layer is brought right at the melting temperature. And as it cools down, as it decreases in temperature from layer, it needs to have the full conductivity, Young's modulus, and all of the properties assigned from room temperature to melting temperature, so it can simulate that area of high temperature. In the engineering library, these data are provided. A simple combination wrench is chosen for the project. This versatile tool may come in handy, keeping in mind the background story of the ANSYS. Defeaturing of parts or segments, such as fillets on the grip side, is done to facilitate contact between base plate and build for computational simplicity. A base or build plate geometry is also designed at a shallow distance, that is 5 mm from z-axis below the wrench, and a gap is kept to generate support. Of all the vastness of the space, this project focuses on the thermal cycle challenge at low Earth orbit. According to J.H. Han and his group, the maximum and the minimum operating temperatures at LEO for the thermal cycling simulation are 100 degrees Celsius and minus 70 degrees Celsius, and no gravity force will be applied for this analysis. One thermal cycle from 100 degree to minus 70 degree and again back to 100 degrees Celsius takes about 64 minutes. So it is safe to assume too extreme radiation as the study suggests. Therefore, we will be considering transient thermal condition 1 at 100 degrees Celsius and condition 2 at negative 70 degrees Celsius. Some of the other assumptions are that the enclosure or room temperature will be 15 degrees Celsius. The bottom of the base plate temperature is set to room temperature. Preheat temperature is taken to be 100 degrees Celsius, and reference temperature for build body wrench is kept equal to the melting temperature of 316 stainless steel. Here the boundary conditions can be seen in the two images. On the left, the transient thermal condition 1, and on the right, the transient thermal condition 2. The static structural analysis will have a fixed constraint at the bottom of the build plate, and all the thermal load from transient thermal analysis is loaded prior to its analysis. Overall, simple boundary conditions have been used because the additive manufacturing build-up analysis itself needs a lot of computational resources. Now for additive manufacturing simulation, as mentioned earlier, in the part details for the build part, the reference temperature is specified to its melting temperature, 1370 degrees Celsius, as you can see on the bottom right figure, to ensure zero strain point when the layers are brought in, and so as it cools off, it will develop negative strain as it shrinks. For base part, reference temperature is kept by environment, which is equal to the room temperature. For additive buildup, the deposition thickness, hatch spacing, scan feed are chosen as shown on the screen. A parch gas with really low convection coefficient is assumed to be flowing over the built as the process runs. As the powder is not directly modeled, a powder property factor is assigned along with an even lower convection coefficient. Body-fitted Cartesian mesh has been used for meshing. It consists mostly of hexahedral elements with faces that are aligned with the coordinate axis. It is used to subdivide support and build region into discrete layers that are all uniform in thickness. These are the superlayers brought in by element birth option, layer by layer. At the interface, it is important to make sure that the supports and the build part, if modeled together using shared topology, that all of the nodes are completely coincident at the interface. And then this will bring in the special build layer by layer all the way through to the top. Projection factor needs to be set to 0. This is a must to force it to have strictly uniform layers. If changed, it will be forced to follow the geometry much more closely, so we will not get even layers and the simulation will not run. Cartesian mesh uses a top-down meshing approach. In this method, the mesher continuously refines the initial grid in a binary fashion in each dimension and eliminating the non-volume cells up to the specified maximum refinement. The Cartesian mesher does not require an existing surface mesh and will ignore meshing parameters defined to control local surfaces. The mesh will be refined until the finest cell size does not exceed the maximum element size specified in the global mesh setup or the surface mesh setup. Individual part maximum element sizes are set after a coarse mesh study with the smallest size allocated to the build part. Normally, the mesh size should be 5 to 15 times the deposit thickness. In this case, the deposit thickness is chosen 50 micrometers, so the selected mesh size is 0.7 millimeter, and for the base body, mesh size is 8 millimeters. The refinement significantly increases the element and nodes. After careful study of the mesh qualities by checking the orthogonal quality, mesh elemental quality, also skewness, and aspect ratio for hexahedral elements, the refined mesh is chosen as final mesh for analysis, although it significantly increases the number of nodes and elements. From the temperature distribution contours for transient thermal analysis, the part on left exposed to higher solar radiation has slightly higher maximum temperature, whereas figure on the right side shows that the temperature has seeped into the built part and the wrench no longer has the highest temperature as the environment facilitates faster cooling. This close-up video of the transient thermal analysis shows more clearly how the birth element brings in layers at melting temperatures and each layer's cool-down process. This is showing the transient thermal analysis of study 2 at -70 degrees Celsius. The heat convergence charts for transient thermal analysis are almost similar, given the similar temperature distribution, but the lower radiation converges ahead of that for the higher radiation temperature. The graph is divided into two parts. On the left side, the build, and on right, with faster convergence rate, the cool down iterations, approximately 162nd iteration onward. For both studies, static structural yielded the same result. In the total deformation of the wrench, maximum deformation can be seen in the shallow, sharp corners on the left side of the wrench. Also, both sides of the wrench has higher deformation. Noticeable, the notch at the top handle is well cured and exhibits no deformation. This is an exaggerated view of the same. Maximum deformation 2.59 millimeters is observed at the top tip of the two edges of the wrench. Static structural shows plastic strain. Therefore, although slight, there is plastic deformation. From an exaggerated view, the maximum plastic strain can be observed at the bottom of the tip of the two edges of the wrench. This video of the static structural analysis shows the equivalent plastic strain more clearly. For the built body, maximum plastic strain is 0.084 mm per millimeter, which is found at the top and in areas of changing geometries. Both solar radiation exposure yielded the same result with the same force convergence graph, which is not very surprising as the temperature distributions were quite similar. The graph is divided into two parts. On the left, the built, and on the right, the faster convergence rate, the cool-down iterations, approximately 230th iteration onward. This simulation study helps in understanding material distortion in additive manufacturing before printing it. That is a huge all-around benefit. From the temperature distribution contours of the transient thermal analysis, slightly higher temperature is found at the top layer of the built body and slightly smaller values of 15.5 degrees Celsius is observed by the built plate. That is the maximum for the second study, specifically at the top layers of the built body near the wrench as the heat seeps through it. The slightly lower temperature is due to the low radiation exposure. Therefore, heat transfer here can be said to be convection dominant, although the convection coefficients were kept quite low. From the exaggerated views, maximum temperature for study 1 is found at the top center layers of the build part, whereas for study 2 it is found at the build plate as the lower radiation facilitates faster cooling. For both studies, the static structural analysis yields the same force convergence, total deformation, and plastic strain, which is not very surprising given the similar temperature distribution found in both studies. Peak deformation of 2.59 mm is found at the two corners or tips of the wrench grip, mostly at the build support interface, most probably due to a low material multiplier factor of the support. It was kept low in order to reduce hardware computational load as additive manufacturing tool with almost 300,000 nodes is naturally computationally heavy. The average deformation is quite small, 0.21283, and on average, the higher deformation is observed at the build support interface. Almost no deformation is seen at the top, and the center notch of the top handle is well cured and also exhibits zero deformation. There is plastic deformation. Maximum value is found on the two corner tips of the wrench at the outermost two elements of the generated support. For the built body, maximum plastic strain is 0.084 mm over millimeter, which is found at its top and in areas with changing geometries. The zero strain set at melting temperature helps in reducing the distortion, but it can be further perfected before actually printing out the product. As future project, similar study can be done by increasing the generator support material multiplier factor to see what changes it brings to the same analysis, but with higher hardware computational capacity. Another study can be done by coupling other relevant analysis systems for further detailed analysis. For example, a coupled thermal electric system or a vibration system, etc. Also, taking on other challenges that the space offers, for example, the vacuum pressure by coupling in fluid flow can also be done. This project was focused on studying an additively manufactured part subjected to two extreme solar radiation cycle in low Earth orbit space with the new additive manufacture tool of ANSYS 2019 R1. Two types of couple simulations were successfully conducted and results were obtained. The temperature distribution in the transient thermal analysis helped to visualize and learn the effect of two extreme radiation temperatures on the build parts. And the total deformation and equivalent plastic strain results obtained from the coupled static structural analysis clearly showed where the manufactured parts developed strain and distorted the most. As a pilot research project, this study has armed us with better knowledge about 3D printing in space, which will further support our research goal in future. In conclusion, a better additively manufactured product can be designed with the help of different tools, for example, topology optimization, based on the knowledge gained from this project. A directed energy deposition system has been modeled since this is the only available additive manufacturing process in ANSYS. However, it is not practical for space, which is a major limitation of this project. Other limitations include the hardware computation capability. For this project, a dual-core processor with 55 GB disk space was used, which was fully consumed while running this process. The compromise for meshing had to be done. Because of the capability limitation, each analysis took almost 14 hours, which is not very efficient. With richer computational resources, even higher accuracy result can be obtained. The additive manufacturing tool of ANSYS is fairly new, and like any other new tools, it also has some glitches for which the ANSYS community is informed. For example, this tool has a additive manufacture sequence option in the mechanical modeler, where other than the build step, the cool down step, removal of base and removal of support can be chosen. But the last two steps resulted in a convergence failure every time. Resetting or cancellation options also stopped working, so the project had to be redone from scratch without selecting these two options. With this, I'm at the end of my presentation. Hope this video was informational and helpful to you. If you have any queries regarding this analysis, feel free to contact me at the provided contact information. Thank you.